on the show, they go,
"Resistance is futile."
And that's Star Trek. Hey everybody, welcome back to another Physics with Dr. T. I'm Dr. T, and this week we're going to do a walkthrough on resistors in combinations, either in series or parallel. This week I'd like to welcome our friend Yong Jin. He's one of the grad students here. And
hi, guys.
And he's going to talk to us a little bit about the equipment you're going to be using for this week's experiment. But before we get into any details, let's talk about this week's PreLab activity. Okay, so you're ready to do your PreLab, and so you click on the link in D2L, takes you to this page, and what do? We have intro and lab. Well, we don't really need to muck about in intro, so let's jump into the lab. And we double click on to launch that. Now you have a workspace that's open. Over here on the left side, you see you have a wire, you have battery. This is basically your toolbox. So you go into your wire, your battery, you go to a light bulb, resistor, switch. Let's click on this down here, and we see that there's a few other variations of the same idea. We don't want to get too carried away. We're just going to build a simple circuit, test it, and move along. And so this is the item. Now you can choose between a classical battery or diagram design battery. They do the same thing, just one looks like a physical battery and one looks like it would in a schematic diagram. Over here on the right hand side, you've got a few operational uses. You've got, you can show your current either as electrons moving, or you can show it as conventional current. It'd probably be a good idea to see it as both. What you print, I would actually think should show as electrons, because while it's good to know current and the conventions on that, I still think it's good to think also in terms of flow of electrical charges. But I'll leave it to you to make that choice. You can use the labels to show and values, which we'll demonstrate those in momentarily. You have a couple of meters down here that you can use. You can use the voltmeter. You got two different ammeters. The one on the left is one that you just put the target over a point in the circuit, and it'll show you what the current is at that point. The other one you physically connect into the circuit the way you do with the other components, and so on. If you click on advanced, it's going to have a few things that you can adjust here. We're not going to adjust that, so I'm going to close that back up. So how do we use this? First thing we do is just go ahead and start bringing stuff onto the floor that we need. So we're going to grab a battery, drag it onto the workspace. I'm going to grab a resistor and a second resistor. I'm going to bring these on out here, and I'll go ahead and bring a switch out here because I'm going to want to control the flow of that circuit. The first step in this PreLab is parallel. So we're going to set these up in parallel configuration. So I'm going to go ahead and shift these, and now they're kind of lined up. You grab a wire and you drag it out. And it might be fine to just grab these and drag them and connect them like this, but you might inhibit yourself on that. So let's click on this. You see that now it comes up, it says, do you want to cut this wire? You click on the scissors and it cuts the wire. You're no longer joined. So we'll put this back over here. And we'll put a wire on both sides of all components that I'll be using. If you want to drag it, you just move it around. Grab the wire, move it out here. I encourage you to play with this workspace. Let's move this up. You see how it wants to join in there, so I'm going to let it join in there, and then I'm going to take a wire and connect it to that end. Connect. Connect. You do the same thing all the way around, and you can see that they have little electrons that are already kind of ready to go. You have to click and drag. I keep not clicking and dragging. Now we have a circuit. Let's close it. And you see electrons are moving. So let's open it back up, and let's click on each component. Here I clicked on the battery. It says 9 volts. According to the PreLab, the instructions are to set this to 5 volts. So we'll come down here. You can click this left and right. You cannot click on here and type it in manually. That's frustrating, but you can also drag the bar. So whichever one is more effective for you. I'm just going to drag it to that point. So now here we are. The battery is set to 5 volts. It's going to supply 5 volts of power to the circuit. First resistor, that needs to be 2 ohms. This one needs to be 4 ohms, and you'll notice that the colors change. I'm going to drag this big time. Look what it does with the colors on the stripes. Each resistor is rated based off of its ability to block flow or its internal resistance. Now, that means that whatever its resistance is, there's a color code that corresponds to it. You can check your lab manual for more details on this, but as you change the voltage here, you'll notice the colors change on the resistor. I'm going to set this to 4 volts according to the lab manual. I promise you, if you set these to much higher than this, then your circuit is going to behave either really boring or really interesting. In the lab manual, the ammeter is set in the circuit. I'm not actually quite so worried about that, so you can just kind of put over top. You see right now, anytime I put over the thing, it says 0. So let's close the switch. You want to grab the target. Target says 3.75 amps there, 3.75 amps there. Right here, 2.5 amps. Right here, 1.25 amps. So their motions are relatively moving, but the amperage is clearly showing a different current in each of these different segments. You bring it onto the other side, you get similar results. This method is a little bit more efficient than doing the in-place ammeter because you are testing the different pathways, so you want to use this targeting ammeter above the other one. Now you drag a voltmeter in place and you can set it. You grab the leads and you place it in one spot and the other, and you can see that it's showing now 5 voltage across the slower resistor. We'll move it here, and now we see another 5 volts. So you can use these details to make measurements as you build these lab manuals. You'll do the same basic process for a series, only in that case you want to put your wire so that the wire connects to one resistor and then to the second resistor in line, just as you see in the diagram in the lab manual. And you make your observations, do the calculations according to the question that's given in the lab manual, submit, and that does it for the PreLab. All right, great. So let's get into a little bit of the theory here behind resistors in combination. Now, previously you've looked at resistors by testing different substances and applying voltage, measuring the current across it, and discovering that certain devices were ohmic. And resistors in particular are a special case of ohmic device whose job is specifically to control the flow of current in circuits. You saw that any device that did obey this ohmic behavior was relating to Ohm's law, V equals IR, which we'll be taking use of today. So let's look at a combination of 2 resistors and start there, keep it simple, and see what we come up with. In this case, we're going to look at 2 resistors set up in series, R1, R2. We have a closed circuit. We have voltage coming from a battery, and we know the current flows from the positive terminal through the circuit. And in this case, we say, all right, well, if I have the voltage of 6 volts, it's got to use up all the energy before it gets done for any electricity that's going through there. We know that we have, say, 6 volts, 10 volts, whatever the battery is holding, even if it's like a 1.2 volt. So all 6 volts have to be used up going across these 2 resistors, so we can add up the voltage across these 2 resistors and get back or use up the energy that came from the battery. And so we write that down. The voltage of the battery is equal to the voltage across resistor 1 plus the voltage across resistor 2. Now, if you're savvy with that, then we apply Ohm's law, because we're dealing with only ohmic devices right now. So for the battery, that's going to generate a total current going through the system, and it's going to come across the total resistance of these 2 resistors in combination, or 3, or 4, or 5 resistors in series, or more. Each individual voltage corresponds to a current across that resistor, and the resistance of that resistor, and so on. So now the next question is, how do we see if we can simplify this? And we look back at the circuit, we say, oh, you know, the current that's traveling through these resistors has to travel through each one of those in order for the electricity to get to the other side. So they're going both through both resistors. That means that the current of the total circuit is equal to the current across each resistor, 3, 4, and 5, and so on. This means that we can cancel all the current in the equation and end up with a definition for an equivalent resistance for a series circuit of resistors, R1 plus R2, and so on. And as always, we want to kind of call back. Remember, we want to fall back on these analogies that are working for us. Think about our water analogy. Well, if water is going out lake physics and it goes through one pond and then it goes through the other pond, if those are conserved quantities in that sense, conservation of matter. And so the analogy holds, continues to hold for us, and that's very nice. Okay, so we just talked about series, but now let's take a look at the other option of combining these, which is called parallel. We call them parallel because the current in our setup now has an option of taking 2 different pathways. Those pathways are parallel to each other before they join back up and return to the battery. So one thing that we know for sure about this is that the total current of the circuit is going to be a sum of current 1 and current 2 which is just, again, another statement of conservation of mass. So we apply voltage equals IR, Ohm's law, again, to each component or each part of this the equation. We find that we have these, what looks like a worse equation than before, but we do have a nice benefit here, and this is something that you're going to test and confirm as you go through your lab activity today. The voltage drop across the battery and the voltage drop across each component in this example is going to be the same voltage. The current is being pushed with the same amount by the battery as it would for each individual. Again, that means that these are all the same voltage. That means we can cancel the voltages out and we get an equation for resistors in parallel, which does not look nice and clean as that for resistors in series. And there's something that often trips students up. You do 1 over resistance 1, 1 over resistance 2, you add those up, you get stopped there, and a lot of people will accidentally report that as a resistance. So make sure you don't forget that once you've got this, you got to take the inverse of that value in order to get your R equivalent. So don't forget about your working with equations with fractions. Again, we take a look at our water analogy. Does this work for water? Well, I think it does. So we have, in this case, let's say a water tower that comes out, and the water has a split between 2 possible pathways for it to go down the pipes, and then it goes into tank 1, tank 2. They may be different size tanks, they may have different size tubes, whatever, but the water goes in there and then eventually joins back up on the way out to the drain. So it works out, again, very similar to what we saw before with series. So let's take a look now at the equipment that we'll be using.
Okay, for this one, as an example, we need to start from the band close to the ends. For this one is red, orange, and silver. And we can get from the table that red is 2, and the orange is 10/3, and the silver is 10% tolerance. Yeah, and then we need to use the multimeter to do the measurements. So for this part, we just need to use the multimeter to use the ohm meter. So for this one, we turn to the ohm meter and do a test on the resistor. And if we need to use ammeter, we need to switch this one to this set. But you need to know that if it is beeping, it means that you are in the wrong place. If you do it right, you won't have that noise. So for this one, for a circuit you can use this. You can change it to use the BNC to instead of this one. This probe should be next this week. So that you can connect to the other things to test the current. Remember that the ammeter should be in the current, not like the ohm meter. It's a different thing. And we will use this one to connect the PASCO to test the voltage. We use this one. This part we need to connect to the PASCO, and this one we will use to test the voltage for the resistor. And you can check the manual for details.
So I want to take just a quick moment and walk through setting up things in PASCO. It can be a little bit confusing if you're not too clear on what's going on, and the description on some of this is not set up yet into the lab manual. So let's just take a quick look at this. So you're in PASCO Capstone, and as usual, we go over to the hardware setup. So you're going to be using PASCO for both a power source and as a voltage sensor simultaneously, just using 2 different aspects of it. So the first thing you want to do is go and turn on the voltage power supply. Again, this is like you've done previously. You click on the single option here at the top and you change it to an output voltage sensor, output voltage current sensor, and you go over to the signal generator and you click on that. This is going to be your output. Change that to DC output, which means constant current going in one direction. We're not using AC. And I believe the lab manual requires you to set this to 6. So you can either double click on this and change it to 6, or you can move it up and down with the little controller here. But now you have 6 volts here, the DC voltage field. Leave the voltage limit at 15 volts. That's a safety setting. and you can turn your voltage on whenever you're getting ready to take data. Now you want to make sure that you keep that off unless you're running the measurements so that you are not risking damage to the equipment or to safety to yourself. So just, be diligent. Now that you have the power supply aspect set up, you can go into the hardware setup again. You're going to look for the port that you plug this into for your voltmeter. And you click on that port. You have a list of different sensors. It's not going to automatically determine this one. You got to scroll down and turn it to voltage sensor. Now you've got the voltage sensor in place. You just go and close your hardware setup. Let's pull a graph onto the workspace. Boom. You right click on measurement and you can see voltage is right there at the top. Make sure you use the voltage sensor voltage. Don't use the output voltage. That's coming from the internal systems, and there are some factors that make that almost always inaccurate. So don't use that. Use voltage only, not output voltage. That's it. Now you're ready to take data. So this week's lab is a worksheet lab. That means that you will take the 2 pages that have the data that you've compiled onto it. Make sure you make your calculations for your percent differences and percent error. Keep in mind that the percent difference is what's written on the page, but the question you want to ask yourself, and maybe even comment on in the summary, is this percentage difference or is this percentage error that you want to calculate? Now, again, you want to determine whether or not you're making the choice based off of the nature of the value you're comparing against. And then, as with all worksheet labs, you want to write up a 1-page lab report. You want about 1/3 of it to talk about the theory. That'd be Ohm's law, talking about resistors in combination for series and for parallel. But for that final 2/3 of it, you want to use that space to talk about the outcome. We're, again, less focused on was it a good experiment, did you enjoy yourself? More importantly, did you demonstrate that resistors in series sum up? Did you demonstrate that resistors in parallel have a summation of 1 over the resistances? Make sure that you don't forget to flip over that resistance whenever you get done with it. And that's it. Just make sure that you're, again, challenging yourself to write a better and better, concise, scientific evaluation of the experiment, its effect on your results, and the validity of your results. Okay. All right, well, that does it for this week's walkthrough. If you have any questions about anything that's going on, make sure that you ask me or your TA, your LA, even talk amongst your classmates. And don't forget that we also have the Physics Help Center over at ID Weeks. I'd like to thank Yongjin for joining us and talking through things with us today. And that pretty much does it. Until next time, we'll see you in the laboratory.
What do you think about this?
Well, that's a big resistor. So as recording, we're going to talk about here. Hello, 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 hello. Okay, so we're going to do resistors in combination. This is the part you say, that's a big resistor.
I don't want to.
I'm ready for my close-up, Mr. Jamil. It's always weird. I have to tilt my glasses up so that the light doesn't reflect off them so weird. But you try always wearing your glasses 1.5 inches above your ears. So I'll say that does it for this week's that does it for this week's walkthrough. I can't even get it right when I'm practicing. Okay, so hey, welcome to another walkthrough. This week we're going to be doing the lab on resistors and things in combination or whatever. Resistors in combination. We got series. We got parallel. My fancy little drawing here. This will work.
Can we skip this one?
I'm afraid not. I love the joke too much. It's a bad joke. It's a bad joke, but it's a fun one.